Okay, so we'll move on and continue talking about circuits. We're going to look at RC circuits today, which is just uh, shorthand for resistor and capacitor based circuits. And one of the things we want to try to understand is like how long does it take a capacitor to charge up? So we know that when we apply a voltage to a capacitor, current flows onto it, but we haven't talked about how that happens. How long does it take before it's fully charged? And so we want to explore that today. Okay, so an RC circuit is when you have a voltage and a resistor in a circuit so that current flows through that resistor. And then if there's a capacitor in the circuit as well, that current can flow onto or out of that capacitor. And so we say it's either charging up or discharging, depending on whether current is flowing onto it or off of it. And we call that an RC circuit. Now, we would expect that charge will flow onto a capacitor until it's fully charged. And the term fully charged means no more charge is flowing onto it. So when a capacitor is fully charged, what do we know about the current in the circuit? Bella? It's in the steady state, absolutely. And if the current is flowing through the capacitor and the capacitor is fully charged, that current must be zero. Okay? Because if it weren't zero, there'd still be charge coming onto the capacitor and it wouldn't be fully charged. Okay, so we can look at such a circuit. So here's a voltage source, and the voltage here is labeled as E for EMF. That's just a voltage. And once this switch is closed, we'll have a complete circuit where current can flow across this resistor onto the capacitor. And so if the capacitor is initially discharged, okay, so that the charge on it is zero, what is the voltage across it from B to C? It's also zero, yeah. So V is Q over C. So if Q is equal to zero, if the charge is zero, there's no voltage across it. So there's no voltage across it. This acts just like a wire. Okay, a wire has no voltage across it either, right? It has the same voltage at every point. So what that means is, if we analyze this using like Kirchhoff's loop rule, what we'd say is we go up in voltage by E, and then we go down in voltage by IR, and then there's no voltage change across the capacitor, and that brings us back to where we start. That is after we close the switch. So the current would just be E over R. Right? We could solve for that. It'd be the same as if that capacitor weren't there and it was just a wire. But of course, that's not going to stay that way because the current that flows onto this capacitor is going to deposit charge. And as it charges up, it starts to get a voltage across it, Q over C. And so as this voltage builds up, we always have this constant voltage E being supplied to the circuit. And the voltage drops have to equal IR, and Q over C is the voltage drop across the capacitor. So as Q builds up, I goes down. And eventually, when this is fully charged, such that the voltage drop across it equals the EMF of this battery, then there's no longer any voltage drop across the resistor, and no more current will flow. Okay, so sort of the two extremes are when we initially close the switch, our discharged capacitor just acts like a wire, and current will flow through it. When it's fully charged, it acts like an open switch and doesn't let any current go through it. And what we want to investigate is what happens in between and how long does it take to get from that initial to that final state. Okay, so let me work through this. We're going to use Kirchhoff's voltage rule going around this circuit here. And so we have a voltage gain of E minus a voltage drop of IR minus a voltage drop across the capacitor, and that has to equal 0. So I'm going to use the fact that the voltage across the capacitor is the charge on the capacitor over C. And I'm also going to use the fact that the current is the time rate of change of charge, dq dt. Okay, so if I plug those things in, I can rewrite my original expression in terms of a single variable, q. Okay, so initially my expression had two things I didn't know, the current and the voltage across the capacitor. Now I have just a single unknown, q. Okay, C is the capacitance. That's something that we could measure or know ahead of time. E is the voltage supplied to the circuit, so that's a constant. And then T is the time since the capacitor started to, let's see, what were we doing here? We were starting to charge the capacitor. So it's the time since it started to charge, since we closed the switch. Okay, so what I'm going to do is rearrange this a little bit. I'm going to bring the dq dt to the other side. And that leaves E minus Q over C. And then I'm going to divide both sides by E minus Q over C and multiply both sides by dt. Okay, so I'm going to multiply by dt over this term in parentheses. And when I do that, on the left, I just get dt. And on the right, I get dq over E minus Q over C. Yeah. Oh, I lost the R, didn't I? Thank you. Let's keep that, because that's worth having. That was there. So so let me rearrange this a little bit more. I'm going to multiply, I'm going to divide both sides by R times C. And so I get dt over RC. And on the right, that R cancels out, and that C cancels that, and I'm left with C times the voltage minus Q. Okay, so that's a form that I can work with. So I'm trying to solve for the charge as a function of time. And what I have here is called a differential equation. It's an equation that has charge and time in it, but it's the derivative of time and the derivative of charge. So in order to solve this, I actually have to integrate both sides to get rid of that differential. And so on the left, I have this constant 1 over RC times the derivative of dt, which is just t. And on the right, I can rewrite this as, let's see, let's let u equal q minus ce. Then this integral on the right is minus du over u. And the integral of that is minus natural log of u. And so let me bring the minus sign to the other side. And remember, I'm trying to solve for q. So the way that I can do that is take e and raise it to the left side and set that equal to e raised to the right side. And so the reason I do that is e to the natural log of some quantity is just that quantity. Okay, and so I can finally solve for q. This is the charge as a function of time equals, whoops, I was a little careless. I did my integral, but I did it as an indefinite integral. I want to integrate from charge 0 to some final charge q of t, and from time 0 to time t. And when I do that, I'm going to get natural log of, let me just back up a little bit. So when I plug in those limits of integration, I have, for the first limit, this expression, and for the second limit, that expression. Okay, and when I subtract natural logs, that's equivalent to taking the ratio of those natural logs. And now I can take e and raise it to both sides. And that will work out a little better for me. Did I switch the Q and the CE? I changed the order and put a minus sign in. So I did switch it, but I added a minus sign to account for that. So that was this expression here. If I multiply both sides by CE, then I can write Q minus CE from the left equals CE times e to the minus t over RC. And finally, Q of t is equal to CE e to the minus t over RC plus CE. Okay, so here's my expression for the charge as a function of time. Or if I like, the voltage across the capacitor as a function of time is just Q over C. So I can write that as E times e to the minus t over RC plus E. Okay, so let's look at this expression for the voltage across the capacitor. At time 0, if I plug in 0 there, this term becomes 1. And I have, I messed up a sign. Where did I, if that is 0, this is 1. I should be getting, that should be a negative sign there for that to work out to be 0. So I've got an error in my math. I don't see it. But the check that I'm doing is I know when I start this with the switch closed, there's no charge on the capacitor, so there should be no voltage. So at t equals 0, this should equal 0. And it's not. It's giving me this term plus that term. Okay, I'll have to find that later. So let me quote what my expectation is. That the voltage across the capacitor is equal to the voltage supplied by the battery times 1 minus e to the minus t over RC. This is the result I was expecting. And I've got it worked out in the notes as well. And we see that form right there. So at time 0, we get 0 voltage across the capacitor. And as time increases, this exponential gets closer and closer to 0. So e to the minus a large number is going to be close to 0. And so the voltage across the capacitor becomes just E, the voltage supplied by the battery. So whatever voltage we put onto the circuit is dumped across the capacitor. Vincent? That E is the, you asked if it was the terminal voltage. This is an ideal battery, so it is the terminal voltage, but it's also the ideal voltage of that battery, the open circuit voltage. Bella? To the what? I can go back, but I know I have an error here because my result had a wrong sign in it. So I think the work here is correct. So I'll have to trace down where that sign error is. Yeah, Noah? Oh, you know where it is. Perfect. Yep. Yep. Oh, the negative right there. Thank you. Yep, that negative right there got me. So that should be negative, and that means I multiply by negative, and that makes everything happy. Uh, all right. It's it will ultimately result in that final expression. So this is the voltage across a charging capacitor. Okay, and what we can see is that the voltage increases to a maximum value equal to the voltage that we put across the capacitor, the voltage source in this circuit. Um, but it actually takes forever to get there. This just asymptotically approaches this final voltage. So we can ask, like, how fast does this capacitor charge up? But we can't ask how long does it take to be fully charged, because it's never fully charged. It just keeps getting closer and closer. Bella? This negative right there uh, came from, well, we had it right there. And we switched the order of the denominator there and multiplied. So we multiplied both sides by -1. So that's where that negative came from. Okay, so if we were to plot the voltage as a function of time, and at time 0, we close our switch, and the capacitor starts to charge, it has this exponentially decaying movement towards this final voltage. So one of the things that we do to characterize how fast it's charging is we talk about how long it takes it to reach a certain fraction of the final voltage. So it's never going to get 100% of the way to the final voltage, but it will get 50% of the way after a certain length of time, and it will get 63% of the way. And the nice thing about 63% is 1 minus 1 over e is about 63%. So if we ask how long does it take to reach 63%, we can just say this term in parentheses has to equal 1 minus 1 over e, which means the argument of this exponent has to equal -1 at that time, and therefore t has to equal RC at the time when it gets to 63% of its final value. So we call that time the RC time constant of the circuit. It's a measure of how fast this capacitor is charging up. And it depends on the capacitance. The bigger the capacitance, the longer it's going to take to charge if the current flowing onto it is the same. It also depends on the resistance in the circuit. So the bigger the resistance, the less current will flow. Therefore, the longer it will take charge to build up. Okay, so the product of a resistance and a capacitance is a time. If resistance is in ohms and capacitance is in farads, you multiply them together, you'll get a time in seconds. Okay, and that's telling us how long it takes this to rise to this characteristic level, which is about 63% of the final value. If we want to figure out how long it takes to charge, let's say, halfway, we can do that. We can set the final voltage equal to half of E, and then solve this expression for t, and we can get a value that's also going to depend on RC, but it's going to be, as we can see from this, it's going to be a little bit less than RC. And we can do the exact same thing with a discharging circuit. So if I have my capacitor fully charged and I suddenly open the switch, or I'm sorry, scrap that. I no longer have the battery here, but I have a fully charged capacitor with charge Q, and the switch is open. The moment I close the switch, the charge on this capacitor can flow through the resistor and around the circuit, and the capacitor will discharge. And I can analyze this circuit using Kirchhoff's rules as well. I now have a voltage across the capacitor and a voltage drop across the resistor. Okay, so here's my voltage drop. Here's the voltage of the capacitor. Again, the current is initially going to be the initial voltage across the capacitor divided by R. Right? So if I know how much charge is initially on the capacitor, I can solve for the initial current. But that's going to be changing as the charge on the capacitor decreases. I'm going to have less and less current flowing. Okay, until finally there's no more charge. So let me again say I is dq dt. And in this case, because the charge is decreasing off the capacitor, dq dt is negative. So in order for the current to be positive, I have to put a minus sign there. And the voltage across the capacitor is Q over C. So plugging those into my Kirchhoff's junction rule, I get this differential equation that I'm going to solve. So first I'll bring one of these terms to the other side, and then I'll divide by dq and divide by q and multiply by dt. And I get this form of the expression where all the q terms are on the left and all the time terms are on the right. So when I integrate both sides, I have dq over q, which is just the natural log of q. And so if it starts with a charge of q naught and it ends with a charge of q of t, some unknown charge at some later point in time, the natural log of qt minus the natural log of q naught is what I get when I do this integral. And on the right-hand side, I'm just integrating a constant from 0 to t. So I get, my minus sign stays, and I get t times that constant, which is 1 over rc. So now the difference of natural logs is the natural log of the ratio. So I can simplify this a little bit like that. And then again, I can take and raise e to the left side and set it equal to e to the right side. And on the left side, I'm just going to get q of t over q naught. On the right side, I'm going to get e to the minus t over rc. So I get this expression right here for q of t, and I've divided the expression by c to get a voltage. Bella? The negative dq over dt up here. So the current in this circuit I'm drawing is going from the positive terminal around to the negative terminal, which is the way it goes. And the magnitude of that current comes from the rate at which charge is flowing off of this capacitor. So the charge on the capacitor is getting smaller. Therefore, dq dt is negative. So in order to make... That's because the current is decreasing, because the capacitor is discharging. So the current comes from a discharging capacitor, so I put a negative sign on my expression for the current. If the capacitor is charging, it would be positive. I'm saying if the charge is going up, if current is positive, charge would be going up if it's a charging capacitor. So I work out this expression here for an exponentially decaying voltage on the capacitor. It started out at V naught at time t equals 0, and as the time gets large, this goes to 0. So if I were to plot that at time 0, right when I close the switch, I have the maximum voltage. V naught was just the magnitude of the voltage source in my circuit. And it decays, eventually getting closer and closer to 0. But again, it's an asymptotic approach. So if I want to talk about how fast it decays, I can define the RC time constant as the time it takes to decay to 1 over e of its final value. It's about 37%. So in both cases, we're getting to about 1 over E, or 37% of the final value. It's just the first time we start at 0 and we ramp up to 37% of 100%, which is 63%. And here we're starting from 100% and we're decreasing to 0. So the RC time constant is the time it takes to get down to about 37%. And so, we can see that when t equals RC, we have e to the minus 1 here. And the voltage is 1 over E times the initial voltage. So let's see what we can do with this. Let's take this circuit here where we've got a 12-volt source, and we're going to connect it to a 100 microfarad capacitor when we close this switch. And when we do that, this capacitor will start to charge up, and the rate at which current flows initially is going to be limited by this 50 ohm resistor. So initially we have this RC circuit right here. How long after, let's see, what is the initial current in the circuit, and how long will it take to reach 90% of its maximum charge? Okay, so okay, so here's the circuit that we've got. So initially, current will flow like that. And I can say that 12 volts, just using Kirchhoff's loop rule, 12 volts minus the voltage across the capacitor minus IR equals 0. So I is the current that flows through that resistor. And what is the voltage across the capacitor initially if this capacitor is fully discharged? It's 0. Okay, so that will go to 0, and I can solve for the current. The current is just going to be 12 volts over the resistance, which in this problem was 50 ohms. And so that's like 24 over 100, 0.24 amps for the current. So I could treat this first part of the problem, what's the initial current, as if this capacitor were just a wire, and it was just letting the current flow through it, because it is. It's letting the current flow through. There's no voltage across it, so it's not impeding that current. The second part of the problem asked, how long after the circuit is closed will it take the capacitor to reach 90% of its maximum charge? Okay, so here we have a charging capacitor, and we have two equations for charging and discharging capacitors. One looks like V of t is equal to V naught times 1 minus e to the minus t over RC. And the other looks like V of t equals V naught times e to the minus t over RC. So you might have these equations and be wondering, okay, I know these are for charging and discharging, but you might not remember which is which. But we can figure it out by just looking at the form of the equations. We know that initially the voltage across the capacitor is 0, and over time it should increase. So we can check. At t equals 0, this term here is equal to 1, and this whole thing cancels and gives me 0 voltage initially. So this function matches my expectation that it starts with 0 voltage. This one, at t equals 0, this term goes to 1, and the voltage is a maximum. So I don't want this one. That's for a discharging capacitor. So let me use the one on the left. And my initial voltage is 12 volts. The RC time constant, well, I guess I'll plug in a number for that later. The final voltage that I want is 0.9 times 12 volts, because I'm asked how long does it take to charge to 90% of its initial voltage. So I can divide both sides by 12, and what I get is 0.9 is 1 minus e to the minus t over rc. Okay, so I can rearrange this a little bit, and my e to the minus t over rc must be 0.1. So at this point, in order to solve this, I'm going to take the natural log of both sides. The natural log of e to the something is just that something, right? It's just the reciprocal function. And the natural log of 0.1 is something I can type into my calculator. So to solve for time, I'll just multiply both sides by minus RC. And then evaluate. I've got 50 ohms, 100 microfarads, and natural log of 0.1. So natural log of 0.1 is minus 2.3. So the minus signs are going to cancel, so that I get a positive time. And when I multiply those numbers together, I got 11.5 milliseconds. So a farad times a ohm is a second. Yeah, Gordon? Isn't it micro? I have, okay, yes, it is, and it's not. The number that I get when I work this out, 50 times 100 times 2.3, 50 times 100 is about, 50 times 2.3 is going to be, what, 100 and something, times another 100 is going to be like, I guess, 11,500 microseconds. Okay, which I can write as 11.5 milliseconds. Okay, so if you're just multiplying the numbers, 50, 100, and 2.3, write out your answer, and then the micro that we have from the farads will keep, and the ohms and the farads gives us the seconds. And then we can convert into milliseconds or whatever is most convenient. So any questions on how we went through that discharging, Vincent? Why do we use V naught here instead of, so V naught is our 12 volts. It's the, I shouldn't call it V naught. I should call it V final, because it's not the initial voltage, it's the final voltage. And we can make the argument that the final voltage must be 12 volts when this thing is fully charged, because it's connected to a 12-volt battery. Okay, so let's see what happens when we take and we flip the switch on this. Okay, so we flip the switch up, and now our fully charged capacitor is going to discharge across this 1 mega ohm resistor. So we want to find an expression for the current through the resistor, and we want to ask how long will it take to discharge to half of its initial value. Okay, so it's a similar situation. I have a discharging capacitor, so this time I'm going to use VC is equal to V naught times e to the minus t over RC. So again, I could go back and take these two equations and evaluate and say which one of these behaves the way I want it to. I want the voltage to eventually go to 0, which is this formula, because as time gets large, this goes to 0. So that's my expression that I'm going to use for this discharging capacitor. And it started with a voltage of 12 volts. And R is 1 mega ohm. So R is 1 mega ohm. C is 100 microfarads. Therefore, RC is 1 mega ohm times 100 microfarads. So 1 times 100 is 100. Farad times an ohm is a second. And a mega times a micro is 1. A mega is 10 to the 6th. A micro is 10 to the minus 6. So those units cancel out. And the RC time constant is 100 seconds. So it's going to take quite a bit longer for it to discharge than the time it took to charge. And that's because it's got this big resistor here, limiting the current. So the current only slowly leaks off this capacitor, and it's going to take something on the order of a minute for an appreciable amount of this current to go away. So let's see, what are we asked? Find an expression for the current through the resistor as a function of time. I have an expression for the voltage across the resistor as a function of time, or a voltage across the capacitor. So let's apply Kirchhoff's junction rule. So here's a loop, and we can say the voltage across the capacitor minus IR equals 0, and solve for I. And since I have an expression for my voltage across the capacitor, I can evaluate that. 12 volts over a mega ohm is going to be 12 micro, and a volt over an ohm is an amp. So 12 microamps is the initial current, and it decays with a time constant of 100 seconds. So I can write that current like this. Where did the what come from? E, this one? That comes from my exponentially decaying voltage across the capacitor, which I plug in here for the voltage across the capacitor that I used in Kirchhoff's loop rule. So the second question was, how long will it take the capacitor to discharge to half of its initial charge? Okay, so charge is voltage times capacitance. And so when the voltage drops to half of its initial value, the charge will drop to half of its initial charge. So really what I can ask is, how long will it take for this voltage to decrease to half of V naught? So I want Vc over V naught to equal 1/2. Okay, so I want 1/2 to equal e to the minus t over 100 seconds. So the way I'm going to solve that is I'm going to take the natural log of both sides. And that's going to give me the natural log of 1/2 equals minus t over 100 seconds. So solving for t, I get 100 seconds times minus the natural log of 1/2. And when I evaluate this, I get about 69 seconds. Okay, so if we're trying to find the time it takes to get to some arbitrary fraction of its final value, we can't just use the RC time constant. That's only the time it takes to get to 1 over e of its final value. But for an arbitrary time, we have to go through and set up our expression, and we'll always have this natural log of some fraction that we have to type in. Okay, so what I would like to do is pass out a worksheet for you to work on with your neighbors. We're going to explore this circuit here and what happens when we close each of these switches in order. So we have some voltage source V, and then there's this resistor R1, and then there's this branch of the circuit with resistor R2 and capacitor C2 and switch S2. This branch has resistor R3 and switch S3, and this one has capacitor C4 and switch S4. So we want to know the current through R1, which is basically the current flowing through the battery. First of all, before we do anything, and then after we close switch 1, and then we wait, and then we close switch 2 so that 1 and 2 are closed, and we ask what's the current, and then we close switch 3 and we ask what's the current, and then we close switch 4 and we ask what's the current immediately after closing this switch. So just remember that when you first change, when a discharged capacitor initially has current flowing on it, it just acts like a wire. And when it's fully charged, it should act like an open circuit and not allow current to flow. Thank you. So you can check your answers with what I've got up here. But the trick to this is just recognizing that when you close a switch, immediately the capacitors just act like they're wires. There's no charge across them. So you can analyze when you close like switch 2, so when 1 and 2 are closed, what you have is just the voltage source sending current through these two resistors R1 and R2, and we get a current that's V over R1 plus R2. After a long period of time, and the capacitor will become fully charged, at that point it's as if you opened the switch because no more current will flow through that branch. So when we close switch S3, now we have current flowing through this path and a current of V over R1 plus R3. And when we close switch S4, now we're giving the current an easy path to go around the outer loop. And so it's just going to be V over R1, this voltage divided by that resistor, and then it just passes through. And eventually, after a long period of time, once this capacitor is fully charged, and all these switches are closed, the only path the current can take is this way. So the very final current through R1 is going to be the same as it is after we close S3. Bella? We can disregard C2 and R2 after S3 closes because we're told that there was a long period of time before we did that. And that is code for long enough for this capacitor to fully charge. So if this capacitor is fully charged, it means it's no longer drawing any current. It's like an open circuit. So it's as if we opened the switch. So no current flows through here once the capacitor is fully charged. Okay, that wraps up our work on RC circuits. So we are going to have our quiz. I'm sorry? That will be posted on Canvas by this afternoon.